Good afternoon, everyone. So it's very happy to share some of my recent work with you today. So my topic is about the multi-objective mechanism design for public good allocation. This is actually based on 5 different papers, and there is joint work with my previous student Chen Zhou, Wen Wei, Chang Juan, also my co-authors, Javash, Michael, and Ying Yu. So first we'll start with the introduction, and then I will actually mainly focus on 3 detailed applications. One is for the vehicle license allocation, one is for the public housing allocation, and the last is for the public goods allocation with social distancing. So the public resource allocation, usually have their a little different from the traditional good allocation. It usually have the supply-demand imbalance, and they're similarly to have lots of agents to participate in this allocation. So the agents are usually heterogeneous. So it has a lot of applications, like what you may familiar with, like their H-1B visa, the school allocation, the housing allocation, or the public beach assignment, or even their vehicle license allocation. They are all belong to the public resource allocation. So the conventional mechanism design for the selling some goods, usually we only consider single objective, right? It's either to maximize our profit, usually we call it optimal auction design, to maximize the revenue, or sometimes we want to maximize the social welfare, so we can use the VCG mechanism. And sometimes we just want to maximize the fairness, so we can use lottery, right? It's absolutely fair. So the conventional approaches we used for allocate goods is lottery, a wait list, right? If it's a dynamic system, people come in line, then usually we use the wait list. And also auction, right, for selling goods, and also the matching mechanism for school. So for public goods here, what we want to investigate is, we think for the public allocation, only consider one objective is not enough. So we need to take consideration of multiple objectives. For example, the efficiency, which include the profit, the social welfare, and also we need to consider the fairness also. So for the fairness in different paper, the literature, there has quite a lot of different definitions for the fairness. Depends on where we applied it, right? So mainly it have 2 different types. One is utility-based fairness, which included inverse-free fairness, right? Egalitarian, proportional fair, or maximum fairness. Another type we usually call it opportunity-based fairness. So we only look at the, sometimes we call it the probability, if one can get good or not, so that can everyone be treated equally or not. So next I will more time to focus on their applications. So the first real problem, we apply the multi-objective mechanism design is for the vehicle license allocation problem. So I think some of you may be already very familiar with this currently, the mechanism currently using in China now. So because of the heavy traffic and also the bad air, the environmental problem, so many big cities actually started the vehicle license control. And in each time period, we only allocate a small number of plates, to the potential car buyers. And a car buyer, must first get the plate, then he can purchase the car and to drive on the way. So currently, different cities actually using the different mechanism. For example, before 2013, Shanghai and also the country Singapore, still using their auction now. So we all familiar with what is auction, right? So it is usually it's a very efficiency, but however, it's maybe not fair for the poor people, right? Because the price is keeping increasing. Lots of people cannot afford it. And another mechanism used currently, is called lottery. For example, in Beijing and in Guiyang. So lottery is like kind of fair, everyone have the same probability, but the problem is it's low efficiency and have very low winning probability. Because of the low winning probability, so everyone want to enter a lottery as early as possible, right? So therefore, more and more people, they are actually not that urgent need a car plate, but they participate in the lottery also. And another problem is there's no value exploration because everyone has the same probability. We don't know the true value of the different participants. So that causes the problem is the waiting time is too long. For someone, it's really need a car, but have to wait for around 30 years in Beijing. So another current mechanism used actually is called the reserved price lottery. For example, Shanghai, currently. So it's like we set some price, so you need to pay at least certain amount, but still the highest one can have the high probability to get the plate. So it's easy implemented still, but however, it's hard to set this reserve price. And also it's no exploration again, and the kind of inefficiency in some way. So later on, like Guangzhou, Hangzhou, Shenzhen, they consider to combine these two together. So they proposed a simultaneous auction and lottery, such that each player actually chooses either auction or lottery first. After they make this decision, they can participate either in the auction or in the lottery. So it considered to be fair and efficiency. But however, the problem is it's very difficult for the normal people to compute the equilibrium. So first, it's difficult for you to make a decision, right? You should enter the auction or lottery. And also when you enter the lottery or auction, especially in the auction, right? What price should you submit? So that is difficult for ordinary people to decide. And actually, it's also difficult for us to find the equilibrium of this game. So how to decide the optimal mechanism for this real problem? We need efficiency, we need fairness, we also want it to be easy implementable. So here the efficiency we consider in our model, we consider just the social welfare. We just total expect social welfare want to be maximized. For the fairness, we choose the Gini coefficient. And the fairness will be just 1 minus Gini coefficient. So what we consider is the opportunity, fairness. Then the problem can be modeled, in this way. We only need to have K, license. That's K good allocated to N players. And each player has a value which shown from a distribution. And the player is risk neutral and with unit demand only. So the optimal mechanism we decided is we want to maximize the objective function because it's multi-objective. So we put the social welfare in the objective function. And then we put the fairness into the constraint. So we want to maximize the social welfare, but with the condition it satisfied a certain fairness condition. So we start with two group mechanism because to solve this optimization problem, it may be turned out to be everyone will have a different probability. Everyone can have a different probability QI. So we start with a two-group optimal mechanism. So in these two groups, it's very easy to implement it and easy for the participant to understand. So it's just we need to divide all the participants into two groups. One group is for lottery 1, the remaining is for lottery 2. But however, the lottery 1 had higher winning probability and the lottery 2 had a lower winning probability. So within each group, every player had the same winning probability. So we need to decide the small k, license to put in the lottery 1, and then all the remaining licenses can be put in the lottery 2. The corresponding transfer payment rule is not difficult to find, right? We just follow the traditional way. We can write down the formula for the transfer payment. So the first I want to mention is that for this two group mechanism, actually it's already can unify the three mechanisms we are using now. It actually already includes the auction lottery and the reserve price lottery. for the last one, the simultaneous auction and the lottery, actually with a very mild condition. The condition is just the participant is, okay, the number of the participation is larger than the number of licenses. Then we can prove, okay, this two-group mechanism, the optimal one among this framework, will be, okay, better than simultaneous auction and lottery. So we just now we just focus on this two-group mechanism. So because it's only have two groups, so we can write the objective function, right? Just the first part, the first term is from the group 1, and the second term is from group 2. Okay, then it's the expected social wear from the both groups with the Gini, okay, inequality requirement. So now we given the distribution of the players, okay, the total number of participants, and also the total number of the license to allocate it, and also the requirement of the fairness levels. We want to find the optimal K and gamma. The difficulties here is the optimal mechanism actually different from all the existing mechanisms. And also the optimal gamma and K, it depends on value distributions. But very surprisingly, okay, we found that for all the common distributions, which include the classical distributions, normal, uniform, exponential, and also the power law relationship like log normal, power law distribution, or truncated normal, even gamma distribution, okay? For all these kind of distributions, the optimal mechanism is always first auctions and lottery. So only two groups. For the first group, the winning probability is 1. It's just an auction. Okay, we just decide the small number K license for the first group, and all the players in the first group, okay, will win 1 place. And then the next group is just the lottery. So this kind of result is like semi-distribution free actually, because we only need to know the shape of the distribution. We don't need to know the mean value. We don't need to know the variance or any other, okay, characterizations of this distribution. Then the procedure is very easy. So the government just decide the license number K and the fairness level, right? And the players just registrate. So after all the players registrate, we will know the total number of participation, the capital N. So then based on the capital N, we can calculate, okay, how many players we will put in their auction. And then the players, okay, can see this information and submit their bids. After they submit their bids, we can decide the winners, okay, payment of the winners in the auction. And of course, all the other players will be in the group 2 and will calculate the probability toward the winner. So this is distribution free, and also, okay, every player is truth forbidden. So to prove, okay, the first auction, then lottery is the best one. Actually, we need several technical lemmas. It's all based on some very important observation. The first one is the relationship between the efficiency and the mean difference. The first, we optimize the efficiency, right, the expected social welfare. And we found that actually, to maximize the expected social welfare is equivalent to maximize the mean differences. Okay? And they actually have the same shape. Okay? And then the second important observation is the relationship between the mean difference and spacing. So the spacing is defined as delta, okay, which is the difference between, okay, two valuation. So the intuition is easy, although the proof is difficult, but the intuition actually is easy to understand. It's just like if we have high probability, right, then like more points will be, okay, around this area. So any 2 points will have a smaller spacing, right? And if it's with low probability, then less points in this area, then we will have large spacing. So after this, okay, we find the spacing and with the relationship of the spacing with the distribution function. Okay, so this is just all the key ideas, the whole picture of the key ideas of the technical part. First, if we find the PDF of the value distribution, then it's okay, tightly related to the spacing. And then for the spacing, okay, we can find the mean difference. And for the mean difference, actually, it can represent the efficiency. So the next question is two groups enough, right? So should we use more groups? So the first is, in this paper, we actually using some real data from Guangzhou government. And we found, okay, for car license allocation, actually 2 groups will be enough, because the differences between 2 groups with the optimal one actually is very small. But theoretically, we still want to know, right, what will be the real optimal, okay, multiple group mechanism for public goods allocation. So we consider the general framework. In this time, okay, we consider it can be any group. And we also extend our definition for the efficiency and the fairness. So now the efficiency, so first is the fairness, okay? It's a generalized Gini inequality, it's not only Gini. So where we will consider permutation of Q and for lower, and we will put lower weights on higher winning probabilities to make them like more fair. And this kind of generalized, okay, equality, actually it includes a lot of special cases which you may be very familiar with, like it includes mean probability, it includes max difference, it also includes Gini coefficient. Also for the efficiency, we extend it to include also can be revenue, it can also be the long-term revenue, it's no longer the social welfare anymore. Then we can have their, okay, general framework, also an optimization problem, right? And we want to solve it. So the main result is, okay, actually at most 4 groups will be enough. We don't need any more than 4 groups. That's already the optimal solution. And in the same group, of course, players have the same winning probability. And actually the first group is option, the last group will be all the losers. So we only have 2 different fractional values, okay, in the group 2 and group 3. And okay, we can prove that we can find the polynomial algorithm to find this allocation. Then the next step, again, for the magnetic area, we need to consider the choose for payment rule. Here, the choose for payment rule, okay, is we don't have any closed form. So we need to decide some algorithm, right, to find the choose for payment. Luckily, we have a polynomial time algorithm. Actually, we can compute the choose for payment. Okay. Then the implementation is very easy. We just allocate 1 item to each player in group 1 because it's just an option. And then for the step 2, right, we just allocate no item to the group 4 because all losers. Then we need to determine the number of items we allocate to group 2 and 3 respectively. So we can conduct lottery within these 2 groups. Okay. So another application, okay, is for the public housing allocation. So for the public housing allocation, so it's also a very, okay, a problem, okay, a lot for researchers actually working on, because, okay, private house is hardly affordable for most residents, and it happens for most big cities. For example, in Hong Kong, more than, okay, 44% of the population living in the public houses. So how to allocate the public houses is a very important problem. Current mechanism is, for example, the lottery in New York and the waitlist mechanism in Hong Kong. So actually we have the result. So the lottery is equivalent to the waitlist. That's why, okay, for our work, we only focus on the waitlist mechanism. So the waitlist mechanism is just like a queue, everyone, right, coming in a queue. And from the bottom to the top, when the people come to the top, we will give her a random offer. Okay, he can choose to accept it, then get the public house, or reject it. And currently in Hong Kong, okay, everyone has 3 choices, like which we call the deferred number is 2, because she can, okay, reject twice. At the 3rd time, if she still reject the option, then she had to leave the queue. So this is the current mechanism. So our focus is on this different number. What will be the optimal different number is 2, the optimal one, or shall we decrease or increase this number? So for this kind of problem, it's also multi-objectives, because we also need to consider the idling waiting time, also the social welfare, and also the matching probability. So we actually, again, we will consider a unified waitlist mechanism, okay? And we consider our agents' optimal strategies and try to calculate the equilibrium state and find the optimal different number. So this can be modeled as a Markov decision process. Then we can write down the value function for each agent. And based on their outside option, because everyone actually has the outside option, right? If she currently not live in the public house, she must have another option, right, currently. So that is called outside option. So when the outside option distribution, is increasing, that means many low need agents, then actually no deferred chances is optimal. But however, when many high need agents in the market, then the infinite number of deferred chances is optimal. For the social welfare, it's always be the infinite number of deferred chances as optimal. But we should also consider workload of the government, because every time when we ask an agent if she wants the house or not, actually the government need to do a lot of paperwork. So this is also something we need to consider. So if we take all this consideration together, we study a case study for the Hong Kong situation, and we found that if we increase the number of different chances from the current 2 to 5, it would increase the social welfare by 10% without violating the government's idling waiting time. Because the times I will be just mainly introduce the main results. If you're interested, all these papers are published, so you can search. The last one is the most recent work about the market for public goods allocation with social distancing. So the social distancing policy actually causing the purchasing frequency or amount constraints in the market, right? Especially because of COVID-19. So like we have the restricted number of people can go to the public place, for example, public library, public beach, right? Not all people can come there, at once. So now the problem is, how to decide who can come. So we use a market equilibrium model. We give the virtual money to every player or every resident, and then can decide where to spend this virtual money. Then the problem can be formulated similar as a official market, but however, now we have the physical constraints. The P transpose xi is less than the A matrix, times the choice allocation x should be less than 1. This is already normalized. So after add this new constraint, we found the problem is like totally different from the traditional fish market. The optimal solution, the characterization of the optimal solution is different. And also, the social problem will be changed. Because before we have a very good social problem corresponding to it, so we can quickly solve the social problem. But now, it's become different. But luckily, we still can prove the existence of the market equilibrium. Now we still can develop a methodology for solving such restricted fish market problem. If you're interested in this work, actually, my course, Devash, this paper is accepted just by Y this time. So my course, Devash, actually have a talk for this paper. So because time, I think I will end here. I'm happy if you have any questions.
Well, I think there are 2 questions from the audience. Let me repeat them. The first question is, in the license place option, what happens if after K is set, then less than K people submit the option Bs?
Because it's like the currently, because you can submit any value, right? You can also submit 0 if you like. If you think you will still have the opportunity to get a license, you can submit 0. That's allowable. but you will maybe have low chance.
Okay, I see. So the next question is, in what measure the waiting list is the same as an auction?
The actually it's no special condition, just it's like when the different number is infinite, okay, it is equivalent to a kind of lottery, and when the different number is equal to 0, it is equivalent to another kind of lottery, because we have two lottery, one single lottery, one is repeated, so everyone can repeatedly to participate in the lottery. So it's just the two endpoint is equivalent to different lottery. But in the middle, for the middle part, if we choose different number, for example 1, 2, 3, then it is not equivalent to a lottery. So that means the wait list actually is more general.
Okay. Thank you for joining the Q&A session. We will have a short break. The next talk will begin in 3 minutes.
Okay, thank you.